So I welcome you all to today's session. So let's start from where we have ended the last time. So okay, so I have recorded the transcript for you also. So without further ado, I'll tell the brief key points from last lecture that we have talked about the Reynolds number and how we have defined that for in-visit and visit flows. So and I have also described the CD versus Reynolds number plot. Then we have seen that the CD decreases with the Reynolds number, and after a very long and high Reynolds number, it shows another dip in the plot. So I will briefly mention some of those. Let me share my screen. So these are from last time. So I have mentioned Reynolds number and the vorticity equations and all. These are some of them. So see it correctly, then okay, so these are the problems I've discussed. So now I'll discuss the screen. So let's talk about the Katta-Joukowski-Lipp theorem. So consider potential inconceivable flow around a sphere. So this is for inviscid flows. This is called KJ-Lipp theorem, KZL theorem, or Katta-Joukowski-Lipp theorem. Okay. So then we get the del square phi is 0, and we know that phi as a function of phi and theta. So define the potential this form, and you are at r is equal to a. You can see the r minus r is r minus r square by r, so 0, and u theta r is equal to a. We'll get that it is r minus a, which is non-zero. Okay, this is how it is defined, the potential form of this theorem. This is clear the radius a of the fluid is in a sphere. You see there's the lines are bent around this basically, right? So this is about the potential incompressible flow around the sphere. So, and if we add the circulation, there will be small viscosity keep between potential flow. So psi r theta will be u r minus a square by r sin theta plus gamma by 2x ln r by a, right? So there is a homework for you. So gamma is a circulation. So ur will be 1 by r del z del theta equal to u. If you just differentiate this equation, you will get this from sin theta, you will get cos theta, and then u theta and del z del r will be this, right? This is theta and this is the r form. Then k, which is the circular integration of u dot dl, that is 8 from r to r on, directly on r minus a square by r cos theta dr, right? Minus this term's integration and this term. So k is equal to, we know the integration of cos theta is 0 and sin theta is also 0. And d theta is 2 pi, 2 pi, 2 pi cancel out, r cancel out, it will be just minus gamma. So gamma is the circulation. Ignore the sign, so it is basically the circulation. So at surface of a sphere where u is equal to u theta, surface where r is equal to a, you'll get that this is r minus a. Okay, and this is r is equal to a. Then on this will be gamma by 2ka, right? Hmm. Using Bernoulli's equation, pressure at surface, stored in viscous flow, P at r is equal to a will be infinity plus half rho u square minus half rho minus 2u sin theta minus gamma by 2ka squared. Then this diagram shows you that sin x at 0, sin 0 0, and this is 3k by 2 minus L. This is basically the, you know all this, right? Sin pi by 2 1, sin 3 pi by 2 minus 1. The sign. So net pressure gradient along y-axis. So you can imagine with a straight invisible flow from the angle, it will be the net pressure under the direction, right? So this is the equation. So net force along y-axis. If you say y-axis, so the net force will be P dot dA. P at r is equal to a times a sin theta d theta, because this is the a sin theta from 0 to 2 pi. It will be P u rho u gamma. Visual flow del dot u is not equal to 0. Propagation of density disturbances. Sound CS square is equal to del P by del rho. For compressive flow, del dot u is not equal to 0. So propagation of density disturbances. Sound CS square is equal to del P by del rho. Propagation of perturbations, split rho Pu into background plus TPS. It will be rho is equal to rho u plus rho 1. P is equal to Pu, P naught plus P1. P is equal to U naught plus U1. Work with a small perturbation sufficient to work at linear order. Background remains unchanged in space and time. Mass continuity equation. We know this del dot LT plus del dot rho is 0, right? From here, if you just replace rho with rho naught plus rho on, you'll get this. So rho naught del dot E1 is equal to 0. Del dot del T. Our equation rho del del T plus rho u dot grad u is minus grad P. So from this, can tell that rho naught del U1 del T minus grad PR. Using P1 is equal to del P del rho 1. So you get this grad square rho 1, the small oscillations equation. And similarly for this, you get this. So at linear order, that means small pressure density perturbations always travel with only one characteristic speed and zero background velocity. CS square is equal to del P by del rho, which is not equal to f omega. I think you understand this because so we're talking about the barometricity, right? So where the pressure is very small and the perturbation intensity is very small, so that it is at linear order. So the zero background velocity, this is the sound speed, is not equal to f omega. Fourier analysis for the dispersion relation tells us that rho is proportional to rho hat exponential of I k gamma minus I omega t. So basically omega square is equal to c square by k square, right? Because k is equal to omega by cs. So phase velocities independent of frequency. Remember this term, phase velocities are independent of frequency and sound waves are non-dispersive. Subsonic flows M is U by Cs less than 1. Quasi-hydrostatic duality is not approximately 0, determined by pressure gradient. Supersonic flow M is equal to U by Cs greater than 1. Quasi-ballistic independent of pressure gradient and BC. If an incompressible fluid is steady, it has to be a subsonic flow. Steady mass conservation at del dot rho u is 0, incompressible del dot u approximately 0. Thus, u del rho much less than rho delta u. So delta rho by rho much less than delta u by u. So steady momentum conservation becomes u dot grad u is equal to minus grad v by rho. So u delta u is equal to minus c square by rho delta rho. So then Mach number is much less than 1. This is the steady momentum conservation. So compressibility is saying that, or its lack of, depends on flow speed versus wave speed. Wave speeds can be super or subsonic in Euler frame. In Lagrangian frame, propagating perturbations are always sonic with respect to background flow in Lagrangian frame. Okay, but in Euler frame, it can be supersonic. Advection equation del rho on del 2 plus rho naught del u1 del x is 0. So rho naught by Cs, this term will be 0. So if you add this term, it will become this, and subtract this from this will yield this term equal to 0. So u1 by Cs plus rho 1 by rho naught is conserved along x minus Cst. It will constant this line. So variation of u1 by Cs plus rho 1 by rho naught and the characteristic ddt of A is equal to del A del t plus del A del x dx dt is equal to del A del t plus Cs del A del x is equal to 0. So this is conserved along x plus Cst is equal to constant. Variation of u1 by Cs minus rho 1 by rho naught along the characteristic. So ddt is equal to del A del t plus del A del x dx dt. That means del A del t minus Cs del A del x is equal to 0. Okay. So E1 by Cs minus rho 1, this is conjugate along this line, and this plus sign conjugate is minus x minus Ct constant line. So why x minus Ct is constant in the forward direction? You have seen there, no? The omega t minus kx minus omega t. Kindly this equation, if you just multiply with k, so kcs will be omega. This is the k exponential omega t. So why this is constant? And show that j plus this term is equal to this. So we have always seen this, that this is constant in the forward direction. Why? We'll just get to see this. P is equal to rho to the power gamma. The parametricity, either P can be proportional, but we have taken the proportionality constant to be 1. So del P equal to P1 gamma rho to the power gamma minus 1 rho 1. So gamma P by rho 1 by gamma P1 by P naught equal to rho 1 by rho naught. Q partitionalized by a diaphragm. So the P1, P2 pressure in region 1 and region 2. So T is equal to 0, P1 greater than P2. E1 is equal to U2 is equal to 0. Suppose diaphragm punctured. Suppose the diaphragm here is punctured now. Say forward wave propagates x is equal to ct, and a backward wave propagates x is equal to minus ct. X is equal to ct is this curve, right? Sorry, x is equal to ct, this is x and t. So x is equal to ct is this one. Yeah, or you can say that this term, depending, you can say 1 by c, right? So and x is equal to minus ct will be this term, this and this, depending on the c or 1 by c. So the backward wavefront is a forward wavefront. So at P, not J plus conjugate along the forward wave. So J plus at t is equal to 0 will be 0 plus 1 by gamma P1 by P2. P2 is the background affected puncture. J plus at xp will be P by Cs plus 1 by gamma P by P2. J minus conjugate along backward wave. So J minus t is equal to 0 will be this minus 1 by gamma. J minus at xp will be this. So if you solve for UP and P, you will get from both this four equation for the piston. UP will start P, P will start P, P not will start piston. And this will move like this. So you will get this. At P,
It's 5 o'clock.
will give this. At P, J minus T is equal to 0, J minus 6P minus 1 by gamma P by Cs minus 1 by gamma P by P2. Three equation, three unknowns value for P, P naught, EP. At piston, J minus is equal to T is equal to TU, J minus T is equal to 0. U by Cs minus 1 by gamma P naught by P2 minus 1 by gamma. The Riemann invariance waves are not weak, not sufficient to linearize. The mass conservation del dot del T plus U del dot del X plus rho del U del X is equal to 0. So 1 by C square you will get this equation. For the momentum conservation you will get similar kind of equation, this del U del T. These are all from the lectures. Combining this we will get this, right? So the quantity U plus A which is vectored forward with velocity U plus CS. This will be equal to 0. The quantity U minus A which is vectored forward to velocity CS minus U. What are the differences with the advection equation? These are for your homework problems. So please try to solve. I'll upload this now. So please try to solve this. So head on to the sample assignment problem. So the first question comes as consider a hypothetical Earth-like planet with an atmosphere of fully ionized hydrogen, which is stratified under the influence of a constant gravitational acceleration g. You can assume that the atmosphere is isothermal. If L is the length scale over which the mass density in such an atmosphere falls by a factor 1 by A, then what will be the correct option? L proportional to T, 1 by T square, or 1 by T square. So you will know that for the isothermal case, P is equal to P follows the ideal gas equation and the barometricity follows rho to the power gamma. Right. So gravitational stratified pressure will be dp dz is g. Right. Okay. So the dp is 1 by p. dp dz is 1 by rho d rho dz, which is proportional to g by t. This here. Gamma is 1. So ln rho proportional to gz by t. So rho proportional to e to the power exponential of gz by t. So E folding length at z proportional to t. This is gz by t, so z is proportional to t. Option A. Okay. A drag force on a solid object immersed in a high Reynolds number flow is observed to suddenly decrease at a critical Reynolds number. This is known as the drag crisis. The drag crisis is due to the sudden drop of the Reynolds number at high Mach numbers, the boundary layer around the solid surface becoming non-laminar. Generation of the small vortices in the boundary layer, non-zero tangential velocity on the surface of the solid body. So if you follow the answer B and C, option A is obviously wrong, and so is option D, because option A is saying sudden drop of the Reynolds number at high Mach numbers. The drag force on solid object is the high Reynolds number, so there can't be sudden drop of Reynolds number. Okay, the drag acid is not due to that. Option D, non-tangential velocity, which is also wrong. The drag crisis is due to the onset of the turbulence in the boundary layer. The turbulence also creates vortices in the boundary layer. Okay. So the boundary layer around the solid surface becoming non-laminar and generation of small water in the boundary layer. These are right options. Next question is pick the correct statement. Vortex setting increases drag on a solid body. A solid body moving in a perfectly inviscid fluid will not feel a drag force. The pressure distribution on the surface of a spinning spherical ball in an inviscid fluid is asymmetric. The pressure distribution on the surface of a spinning ball in an inviscid fluid is asymmetric. So option C, the pressure distribution on the surface of a spinning ball in an inviscid fluid is symmetric. This is wrong because this is asymmetric, right? Because the initiation of vortex shedding is the processes which increases the drag at high Reynolds number until the drag crashes sets in. Okay. Option B is quite obvious because solid body moving in a perfectly inviscid fluid will not feel a drag force. Obviously, because this is valid for fluid. The spinning ball will feel a lift. In other words, the pressure is different on the top and bottom. It is asymmetric. So option A, B, and D are correct. Consider the next question. Consider 2 points A and B inside a gas fluid with a constant velocity. A and B are not close to each other, but pressure fluctuations generated at A can reach B. Choose the correct statement. The flow between A and B is supersonic. A and B are causally connected. The frequency of sound waves heard by an observer moving with the fluid will be the same as that heard by an observer in the lab frame. The frequency of sound waves heard by an observer moving with the fluid will be different from that heard by an observer in the lab frame. Okay, so 2 points can be inside the gas flowing with a velocity. So they're not close to each other. So the pressure fluctuation generated A, so that can reach B. So to clarify this, you can see that the flow between A and B can be supersonic where they're flowing with a constant velocity. Since the pressure fluctuation can reach from A to B, and they are causally connected, and the flow between them has to be subsonic because they are connected, right? It can be supersonic. Okay. Since the fluid is moving, there will be a Doppler shift. So the frequency of sound waves heard by an observer moving with the fluid will be different from the heard by an observer in the lab frame. So Doppler shift is there. A and B are causally connected. Yeah. So it is not supersonic, it is subsonic. The frequency of sound wave not same. The Doppler shift. So option B and D are correct. Consider the following on-day advection equation: del alpha del t plus u del alpha del s equal to 0. Where alpha is some parameter, u is the on-day velocity. Pick the correct statement. Alpha is conjugate along the characteristic curve A is equal to x minus ut. Alpha is conjugate along the characteristic curve B is equal to x plus ut. One can construct an ordinary differential equation from the advection equation with b squared independent and a squared independent. So either a and b or and c and d can be correct. See, remember this is plus, so obviously a is correct. Looking like this, but let me show you that change in alpha x minus ut is constant. Okay. Next thing is del alpha del t. If we do this, will be 0. Del alpha del b will be 0. So del alpha del b square proportional to del alpha del b square is 0. So del alpha del b square 0. Okay. So option C and D both are correct. So next question number 5. Consider a set of undecoupled equation. Decoupled equation. Coupled equation means if one and if one consider if one has if and both it's x and t, and this is also. So if one is equal to this and this is equal to 0, this set represents heat equation, wave equation, nonlinear, none of the above. I think you can guess. But still heat equation is del f del t, a del square f del x I square. Wave equation del 2 f del t square is equal to del t f del x I square. Nonlinear equation is del f del x is equal to f square. So given del f del t plus c del f del x is f1 and this 0. So if you take in the partial derivative the time, you will get this plus, because f1 is this, right? So replace, so put the value of f1 in this equation, we'll get this. and this will be del 2f del t2, and c del 2f del x del lt. So this will be 2a terms, and c square del 2 del x2. So we'll get this. So you can see that this doesn't follow the heat equation, not wave equation, nor nonlinear equation. The mix of them. To couple of the equation to see the only possible answer is D. Okay. So these are the options. So till now we reach here. So this question is very easy. You have to remember the heat equation where del F del T is this is the single derivative. It will be equal to double derivative of x. And here the wave equation is you see in the del 2 some parameter del 2 a del square f. Right? There will be some constant term. There can be some constant term beforehand like k square or lambda square. It doesn't matter though. There can be c to match the dimension. Yeah, obviously there will be c. So x is equal to ct. So there will be 1 by c square and your term. So nonlinear equation, there will be nonlinearity. So this follows del 2a del t2. There will be this combined coupled term. So this is follows a mixed equation. This is basically damped or forced equation, and that topic is out of the scope for this course and session. So we won't discuss that. Yeah. So let's look at the other thing. This question is question number 4. We also following the one convection equation. And then we have number 4, del for del t plus u. Okay. So and then the question number 3, inside the gas flow in the constant velocity push each other, but pressure fluctuations can reach there. So you can understand. Suppose in fluid there is some fluctuation at some point, and that will, if that reaches immediately with another point, so that means the fluid is subsonic. So before the information gets there, the fluid is connected, so the pressure is balanced. So that's why for coily connection there should be subsonic, and Doppler shift will obviously be there. The question is simple if you think that way. The vortex setting, you have to understand the idea of this. And this question, the drag crisis, you have to drag crisis, vortex setting, is a very important phenomena, and this will uh, lead you to the idea of turbulence. If you do any further course on turbulence and nonlinear physics, you will need to know all of this. I mean, in astrophysics, you will need this. This will be helpful. The upcoming ones. So yeah, still now we have discussed this, and this is the sample where the length scale is proportional to the temperature. You have done this in the earlier session also. That's all from this. Okay. So I think you understood. So if you have any question, please let me know. I'll be waiting some time for your question. And for this now, I'll recap some of the earlier portions. That helps. The earlier sessions. Okay. So 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 the next question says, on the key steps linearizing is neglecting the product of small quantities. For instance, linearizing the momentum equations rho naught plus rho 1 del u 1 del d plus rho naught plus rho 1 e1 dot grad e1 equal to minus grad p1. Okay, so the product of small quantities. So for instance, linearizing the momentum equation rho naught plus rho 1 del u1 del t plus rho naught plus rho 1 e1 dot grad e1 is minus grad rho e1. When you neglect the second term on the LHS, consider a body that measures 10 meter atomic cube moving through a medium. The typical macroscopic time scale for the problem is 2 minutes. How large would the velocity disturbances E1 have to be so that the linearizing assumption is not valid anymore? So there is a hint that you can use approximate like del t approximately 1 by t and del x approximately 1 by l, and L are not representative time scales and length scales. So E1 is greater than equal to 0.83 meters per second, and these are the options. So suppose that E1 dot grad E1, the order of E1 is square by L, right? And del E1 del T is and del E1 and del E1 del T. In other words, for E1 exceeding L by T, 10 by 2, so 5 meters per minute. Okay, so option C or 0.083 meters per second. Both are the same, just 10-minute conversion. So assume that the dense plasma at the center of the sun is made up of equal number of density. These are the questions we have this. So the given that pressure at the center of the sun is around, so we know the rho is 129 gram per centimeter cube. That is 6 nmp. So rho will be the 6 nmp, which gives n is equal to, because rho is nmp, right? And we have the 6 number. So which gives n is equal to this, p is equal to, nkt. So which gives the value of p to 9 per centimeter square. If you convert that to atmosphere, we'll get 2.84 because on 9 per centimeter square 1.013 10 to the power 6, right? One atmosphere is equal to the sound speed gamma p by rho to the power half, that is 181 kilometer per second. Option B and option C both are correct. Consider two sources of sound that are equidistant from and stationary with respect to an observer. Source A emits sound waves at 1000 Hz while source B emits at 10,000 Hz. Pick the correct statement. The observer will hear source A earlier than source B. The observer will hear source B earlier than source A. Observer will hear this. So we know that this is a Doppler effect. Sound waves are always longitudinal. Sound waves are dispersionless. All frequencies travel at the same speed. So observer will hear both sources simultaneously. Okay. So they are equidistant. Consider two very large containers A and B filled with nitrogen. The temperature of the gas in container A is 4 times that in container B. The number density in container A is lower than that in container B. So the correct statement. The adiabatic sound speed and called, which is the small and large. So the square of the adiabatic sound speed is gamma p by rho. You see, C square is gamma p by rho, and p is equal to nkt, right? And rho is equal to nm. So n cancels out gamma kbt by m, where rho is the gas density. Number density, we know these factors. M is the molecular mass of the gas, K is the Boltzmann's constant, T is the temperature. So the sound speed depends only on temperature. We know that, not on the number density. Sound waves are longitudinal, so density displacement due to sound waves are in the same direction as that of the direction of sound propagation. So that is longitudinal. Option B, that the attributive sound speed container is 2 times larger than that in container B. Okay. In both containers, the density displacement due to sound waves in the same direction. Okay. So we have this, because this is the 4 times, no? In the square, root over 4 is 2. In the correct statement, very subsonic flows are approximately hydrostatic in nature. Highly supersonic flows can contain discontinuities such as shocks. So highly supersonic flows are affected by large scale pressure gradients. The inertial term in the momentum equation determines the pressure gradient term for subsonic flow. So very subsonic flows are approximately hydrostatic in nature. We know this. And highly supersonic flows can contain discontinuities such as shocks. Okay. I think we have already come across the terms like shock, so you'll understand this. They're very basic questions and equations. That this is the very important thing. The density displacement due to sound waves are in the same direction that of the direction of sound propagation. Please try to remember this. And these are the other equations. So I hope you have had a good session and I'm being able to tell you the things I wanted to. So okay. Thank you. So let's next time. Okay. Bye. Thank you. Hello everyone. So welcome to today's session. So I hope you all are okay and doing well. So I hope you are getting a good pace of your lectures in this course, and you all are getting more prepared for your exam. Wait for some more time just to join. Meanwhile, to
It's 6 o'clock.
for some time. Okay, so where are we? So last time we discussed about socks. Not elaborately, but briefly, we have talked about in some assignment question what socks are. So basically, socks are discontinuities developed in supersonic flow. So you can actually, I have done some of my works in my PhD regarding socks. So this is a very interesting phenomenon. Socks are everywhere, you know, like when you slam a door, like glass, it will also shock. There is a shock propagate. Or if you like drop a pebble into a pond, you see tiny little wave propagates. So the pebble pull a force along the water, and there a shock creates. Or more better intense example will be the blast like Hiroshima and Nagasaki, two of humankind's most indigenous events. So they create some shocks. So basically, shocks are discontinued to develop in supersonic flow. It has some finite thickness and near shock viscous terms relevant. Okay, for shocks in steady flows, viscous effect is equal to inertial term approximately. So rho u dot del dot u. Let me show in rho u dot del u approximately mu del square u. So rho u times du dx is approximately mu times d2u dx2. So no ideal discontinuities in real life. Finite thickness will be mu by u. Okay, so delta. Less viscous fluids, thinner shock. So as the viscosity is less, the shock will be thinner. Faster flow, sharper shock. Shock will be sharp. Now, and will be centimeter square per second proportional to lambda u average, that is proportional to lambda u RMS proportional to lambda CS. Okay. For shocks in mildly supersonic steady flows in approximately 1. That is neither subsonic neither supersonic. It's basically at the Mach level 1. So initial term approximately pressure gradient term. So rho u du dx approximately dp dx is equal to cc square d rho dx. So then rho u square by delta will be equal to cc square by delta. It will be u is equal to cs. Shock thickness is equal to mean free path. So lambda is equal to, I already told you, delta is equal to this nu by u, which is nu by u average, that is lambda. Because u average is uh, yeah, cs. So yeah, that will be like that. So then that is approximately lambda. So basically, shock thickness will be the mean free path. We know the mean free path. The idea of mean free path is suppose there are two atoms. So two atoms collide, right? So the average distance. So the distance between these uh, two particles before they collide is actually free path. If you consider ensemble of particles, then the average of that distance is mean free path. That is said that within that distance they don't collide, so that they are free to move. So basically shock thickness is approximately mean free path. Okay. From here, nu by u average is lambda. Okay. Shock jump conditions for normal shocks. Rapid stream. So zone 1, this is zone 1. The density here is rho 1, pressure is P1, velocity is U1. This is the shock front. And the velocity here is U2. This is zone 2. So rho 2 and P2 corresponding density and pressure. So zone 1 is fluid approaches shock front with velocity U1. Pre-shock fluid zone ahead of shock. So pre-shocked fluid, this is the zone 1. Zone 1 is the pre-shock. So suppose here the shock front generates a shock front propagate like this side. So this is the shock free zone. That's why called pre-shock, before shock. Zone ahead of shock. This is called ahead. You can think it behind, but actually because it is ahead of shock, shock yet not generated. So ahead of shock. This is zone 2 is downstream, where fluid leaves shock front with velocity U2. Okay. With the post-shock fluid or zone behind shock. Shock passes through fluid to convert supersonic flow to subsonic. Shock passes through fluid to convert supersonic flow to subsonic for normal shock. So mass flux conservation is there. Rho1 U1 is rho2 U2, obviously. All your equation is there. P1 plus rho1 U1 U square is equal to P2 plus rho2 U2 square. Okay. Energy conservation is there. Half U1 square plus omega 1 equal to half A2 square plus omega 2. This is the kinetic energy, potential energy, or internal energy. Kinetic energy also can be bulk motion of energy. This is the similarly for post shock. So omega is equal to gamma by gamma minus 1 p by rho. Okay. So the internal energy can be calculated like this. So from Bernoulli equation, we get that omega is equal to integration of dp by rho, right? So now for barometric fluid, P is equal to rho to the power gamma. So dP is equal to gamma rho to the power gamma minus 1 d rho. Okay. So then omega will be gamma root to the power gamma minus 2 d rho. That is gamma by gamma minus 1 root to the power gamma minus 1. Root to the power gamma by rho. Root to the power gamma is P. You can consider here C also, that doesn't matter because C will be just constant. So here again it will be this only. So sorry, omega is equal to gamma by gamma minus 1 P by rho. Okay. That is the internal energy. Shock jump conditions again. Derive rho 1 by rho 2 is gamma minus 1 by gamma plus 1 plus 1 by m square 2 by gamma plus 1. So this will give P1 plus rho 1 U1 square by rho 1 U1 equal to P2 plus rho 2 U2 square by rho 2 U2. Here S1 square is equal to gamma P1 by rho 1. And this is 1 by gamma CS1 square by U1 is equal, plus U1 is equal to 1 by gamma CS2 square by U2 plus U2. E1 minus U2 is CS2 square by gamma U2 minus CS1 square by gamma U1. Which is again similarly on half E1 square plus gamma by gamma minus 1 P1 by rho 1 is equal to half U2 square plus gamma by gamma minus 1 P2 by rho 2. So this then again becomes half E1 square plus 1 by gamma minus 1 CS1 square is equal to half U2 square plus 1 by gamma minus 1 CS2 square. So is equal to gamma plus 1. It should be this CS1 square is again lambda square gamma plus 1 by 2 minus 1 square. This yes 2 square is this. So we'll get that from here. You understand now from where you get. Here you have this conservation equation and you have this conservation equation. Remember CS1 square for this zone will be gamma p1 square by rho 1. Gamma is same because the fluid did not change from monatomic to diatomic. It remains same. That's why. Shock jump conditions using equation for U1 minus U2 will be 1 by gamma U2 lambda square gamma plus 1 by 2 minus U2 square gamma minus 1 by 2. Similarly, this. So, okay, then this become U1 minus U2 lambda square gamma plus 1 by 2 gamma 1 by U1 by U2 plus gamma minus 1 by 2 gamma is equal to 1. So 1 by U1 by U2 is equal to gamma by gamma plus 1 by lambda square 1 minus gamma minus 1 by 2 gamma is equal to 1 by lambda. Which again on U1 U2 is lambda square and tail relation. Okay. So then you get this relation, Prandtl relation, that U1 U2 is equal to lambda square. This quantity lambda is very much interesting. You will see this is the constant that we have added. So then the shock jump condition again will get the CS square by gamma minus 1 plus A square by 2 gamma plus 1 by 2 gamma minus 1 lambda square. So we'll get this E1 square by lambda square gamma plus 1. From rho 1 E1 rho 2 E2 we get that rho 2 by rho 1 is E1 by E2. E1 square E1 E2 so E1 square by lambda square. Using M is equal to E1 square by CS1 square. We will get that rho 2 by rho 1 is gamma plus 1 from here. This is the rho 2 by rho 1 is E1 square by lambda square. Okay. So put here. Okay. So we'll get rho 2 by rho 1 gamma plus 1. This is M square. And actually we need to divide by this term, right? So you'll get U square by C M square. 2 plus M square, here M square. And this is E1 by U2. So if we draw the graph here, if you draw the graph here, a log of ratio and the Mach number plot, will get that for rho 2 by rho 1, right? This will be the graph. Rho 2 by rho 1 with M1 will be this. Similarly, for V2 by V1, we'll get this. For P2 by P1, we'll get this. This is very important for this is for monatomic gas, which have gamma is equal to 5 by 3. So then, so also we have this. So then P1 by rho 1 E1 square, rho 1 E1 plus E1, this U2. So this is basically P2. Okay, P2 minus P1 will get E1 minus U2 times this rho 1 E1. Rho 1 E1 and rho 2 U2 is same. So you can interchange them. So P2 by P1 minus 1 is gamma E1 square by CS square, right? Because rho 1 is so E1. E1 is common, so E1 square. And rho 1 is gamma by CS1 square. CS1 square is gamma P by rho, right? And we have common here P1. So rho 1 by P1. So we have this. The simple calculation you can do it. I think you should do it. Your homework. P2 by P1 minus 1 is gamma m square. This is again m. 1 square is 1 square. 1 minus 2 plus. We have put this equation u2 by u1 is 2 plus m square gamma minus 1 by m square gamma plus 1. So we'll get this. So P2 by P1, 2 gamma by gamma plus 1, m square minus 1 plus 1. Basically, the idea is to represent in terms of the ratios. P ratios of P, ratios of rho, ratios of U. You can see na P, rho, U, and T also there. Right. So the idea is this. Again, we have done this for temperature also. So we know rho P is equal to rho RT, right? P is equal to rho RT from NKT, rho RT. So T2 by T1 is basically P2 by P1 rho 1 by rho 2. So just put the ratio equation. All are functions of Mach number only. Okay. Transonic flows and application. Continuous transition of subsonic to supersonic fluid. Consider flow cross section changing. Steady fluid. Mass continuity equation rho AU is equal to constant 1 by rho d rho dx plus 1 by u du dx plus 1 by u du dx is equal to 0. Our equation says that rho del t plus rho dot grad u minus is equal to minus grad p. So rho u du dx plus dp dx is equal to 0. Rho u du dx plus c square du dx is equal to 0 minus u by c square du dx is equal to 1 by rho d rho dx. So using in previous equation 1 by u minus u by c square is equal to du dx is equal to minus 1 by a dA dx. The flow cross section changing. So then again transforming flows and applications will get basically transforming flows is continuous transition of subsonic to supersonic flows. So the cross section changing. Mass quantity equation there or equation there. And previous equation will get this. The area is changing. See dA dx. Okay. So this flow application is 1 by u m square minus 1 m square minus 1 du dx because cs u by cs square is m square equal to 1 by a du dx. So this relates flow velocity changes to changes in flow cross section correspond to a certain flow. You can see, right? If okay, I'll explain in a bit sometime. Since u a greater than 0, u greater than 0 because velocity can't be negative. A is also greater than 0 because area can't be negative. So subsonic flows, above the flow is now subsonic. Subsonic means m less than 1. So this side is negative. Okay, we'll get this side is negative. So then dx is net, so area is decreasing. So subsonic flow accelerate in converging channels, and suppose area is decreasing. Okay, so as area is decreasing here, a is decreasing, dx is decreasing. So then it will accelerate, whereas supersonic flow decelerate. You can check here. Suppose from here Mach number is less than 1. This side is negative. This side has to be negative. So A can't be negative. So dx is negative. So area is decreasing. Okay, and when area is decreases, then at some point A decreases, decreases. Is decreasing. This means M is M has to increase now. So M increases as area decreases. So speed will increase. Some point M will be 1. There will be some trans point. Okay. So then acceleration decreasing with respect to space. U increases with x. Okay. So now U increases. So M will be greater than 1. And now if m is greater than 1, then this is positive, this side is also positive, so area is increasing again. So D-level noise, this is called D-level nozzle, a clever combination to accelerate subsonic steady flow to supersonic. So with this kind of area area changing scenario, we can transform subsonic flows to supersonic. Okay, so continuous transition to subsonic supersonic flow, transonic flows, how it can generate. So transonic flows in application astrophysical jets. Astrophysical jet, we see this kind of flow when the flow is getting supersonic. Spherically symmetric accretion, black hole or emission solar wind of matter where fluid approximation holds. Mass conservation rho u r square is constant. R is basically so r square or spherical 4 pi r square, right? So 4 pi is constant, so we just take rho u r square. So just taking derivative with it, so 1 by rho 0 dr plus 1 by u du dr plus 1 by r square d dr of r square is equal to 0. So 1 by rho d dr 1 by u plus 2 by r is 0. This will be 2r. So if this is 2r, so r cancel out, it will be 2 by r, right? So Euler equation with body forces like gravity force, that is rho del u del t plus rho u dot grad u is equal to minus grad p plus rho g. So rho u du dr plus dp dr is equal to minus rho gm by r square. It is the gravity g is equal to gm by r square. So rho u du dr plus c square d rho dr is minus rho over gm by r square. So 1 by rho d rho dr is equal to minus 1 by c square gm by r square minus u by c square du dr, right? So transonic flows and application. Using the previous equation, we get that du dr is 1 by u minus u by c square plus u by r minus 1 by c square gm by r square is equal to 0. So du dr u minus c square by u is equal to c square by r minus gm by r. So valid transonic flows transition via m is equal to 1 at some r. Sonic point is when demand finite du dr. So r is equal to gm by 2 c square. Okay. So I think we have understood how this transonic kind of flow this work. So yeah, so this r is gm by 2 c square. C square is gm by 2r. Okay. These are some applications using gravity, astrophysical jet, or spherically symmetric accretion for black hole or emission for solar wind or matter where fluid approximation holds. Okay. So before heading on to the assignment problems, so I think we should spend some time here to understand. So this is a very important non-level nozzle. So I think okay, I'm leaving the slide here to give you some time to understand it. Okay. So I hope you have able to understood these parts. So we have some assignment problems like choose the correct option. See, in real life, the thickness of a shock front is much less than the mean free path of the gas particles or comparable to the mean free path of the gas particles. A term involving del square U and the NS equation is negligible near the shock. The shock results when the forward and backward characteristics cross each other. So I think you can guess one option from here, option B, because that is the only correct option. Shock thickness is the order of mean free path that we have calculated. Since the shock is defined by abrupt jumps in all physical quantities, including velocity, a term involving the risk is actually very important near the shock. Okay, we have the jump in those terms. The shock results when two forward characteristics or two backward characteristics intersect. Okay, not like when forward and backward. When forward and backward actually intersect, they form a cocoon. That is out of the syllabus here. Consider the following 3D wave equation del square delta 2 is c square del square f. Assume this system to be spherically symmetric. Del square f only depends on the radial component r. Also consider another equation which can be computed from the wave equation. Del square g is delta 2, c square del square g delta 2. The relation between f and g is f is equal to rg r comma t. F is equal to 1 by rg r comma t. F is equal to r square g r comma t. F is equal to 1 by r square g r comma t. Okay, so we have this wave equation and this. So you know, del square f is equal to 1 by r square del del r. The wave equation r square del del r is equal to 1 by rg del square r. You can derive it to be 1 by r del 2g del r2. So the relation between this you can clearly see this, right? Moving on to the next question. Question is shock formed in an ideal gas of some finite temperature T. Choose the correct option. Assuming that the speed of the gas flow remains unchanged. The shock may disappear if the temperature of the gas is increased sufficiently. The shock thickness will decrease with increasing T. The pressure behind the shock will increase with increasing T. All of the above statements are false. So finite, assuming the shock may disappear, the temperature of the gas is increased sufficiently. Okay, I think you can guess. The shock, the sound speed CS will increase with an increase in T, right? Because sound speed only depends on the temperature. Since the gas flow speed remains unchanged, the Mach number will decrease and the flow may become subsonic beyond a certain T. Okay. The shock will disappear. The shock thickness for an ideal edge is approximately few times its mean paper, and we know that lambda increases with T. From our Rankine-Higginson shock jump conditions, one can conclude that is as M decreases, P behind by P forward decreases. Okay. P behind means the front of the shock and P forward means the pre-shocked. So option A. Okay. Next question for an ideal normal shock. The normal component of velocity, the component perpendicular to the shock surface, is continuous across the shock. For an ideal monatomic gas, which will have gamma is equal to 5 by 3, the density jump across the shock cannot exceed a factor of 4. The enthalpy of the gas is conserved across the shock. The tangential component of velocity, the component parallel to the shock surface, continues across the shock. The normal component of velocity, the component perpendicular to the shock surface, is continuous across the shock. No. This is the correct option that for an ideal monitoring gas, the density jump across the shock cannot exceed a factor of 4. So you will get this for monitoring gas. You know gamma by gamma minus 1 is 5 by 3 by 2 by 3, 5 by 2, right? But sorry, but gamma plus 1 by gamma minus 1, how much is that? 5 by 3 plus 1, 8 by 3, and gamma minus 1 is 2, 8 by 2, 4. So that is the condition, cannot exceed the factor of 4. D is right because the tangential component of velocity, the component parallel to the shock surface, is continuous across the shock. Okay, the component parallel to the shock surface is continuous. They don't change. Only the perpendicular velocity is change. Consider an ideal gas passing through the Day level nozzle such that the flow transitions smoothly from a supersonic flow to a subsonic flow. One can also use this setup to have a flow transition smoothly from a subsonic flow to supersonic if the flow passes smoothly to the critical point or the flow speed equal to the sound speed. Cannot be so if the flow passes smoothly through the critical point. There has to be a shock. It is not possible to use the same setup to have a flow transition smoothly from a subsonic flow to supersonic flow. So D-level nozzle we know, we have already discussed that it is reversible. So it can be like this, it can be like this. It's the same, right? The flow passes smoothly through the critical point, there is no shock by definition because m is equal to 1. So is there, one can also use the setup to have a flow transition smoothly from a subsonic flow to supersonic. Obviously, if the flow passes smoothly through the critical point, they can, but okay, let me tell you, but if you pass the supersonic flow, it won't be supersonic, it will be subsonic flow. Though there is some certain conditions, car conditions, but okay. For now, let's think that it will be less. So I will again discuss this question. If you have any problem, so let me know in the comment section or in the group forum or the next class. Okay, thank you. Okay. So I have mentioned Reynolds number and the vorticity equations and all. These are some of them. The fluid will flow with an expected velocity given by Vxa for some time for anyone if they have any doubt.
It's 7 o'clock.